In this episode, a record-breaking radio telescope of astronomical proportions.
The first telescope is the largest ever built.
Space-age engineering that is out of this world.
Those sensors can be located to within 1 centimetre in this 500-metre dish.
And the innovative pioneers of the past.
Believe it or not, these are sound mirrors. Amazingly, all of these complex mechanisms are actually governed by a few simple cards.
Who made the impossible possible. Physicist Andrew Steele has travelled to remote rural China in search of a modern engineering wonder that could one day provide the solution to the greatest mysteries of outer space. And this potential key to the cosmos lies hidden from view, seemingly in the middle of nowhere.
Here, in the Guizhou province in southwest China, tucked into a natural basin, sits one of the world's newest and most advanced space exploration devices.
That is an incredible piece of engineering.
The 500-metre aperture spherical radio telescope, or FAST for short, is the largest and most sensitive single-dish radio telescope in the world.
It can pick up radio waves from billions of light years away and will help to unlock the secrets of our universe.
A radio telescope senses the radio waves that objects in space emit, enabling astronomers to effectively see what's out there. And completed in September 2016, this $180 million feat of engineering will probe deeper than any radio telescope has done before. He may be one of its creators, but for astronomer Peng Bo, the FAST telescope still has the power to astonish.
This is the most amazing telescope in the world. The collecting area is more than 30 football fields. If we fill the big dish with wine, everybody in the world could have 4 bottles of wine.
This gigantic 500-metre diameter antenna is constructed of 10,000 steel cables weighing 1,600 tons. On top of the steel spider's web sit 4,450 triangular panels. At the centre, suspended from 6 100-metre high towers, hangs the 30-ton receiver cabin. And it can collect data from billions of light years away. But building a project on this scale is no easy task.
When we proposed such a big telescope, there would nobody believe this big dish can be built.
The first problem engineers had when constructing this thing is its sheer size. FAST is vast. And to put that into some kind of context, the previous world's largest radio telescope was 300 metres across. This thing is 500 metres. That's over twice the area for collecting those faint radio waves coming down from the sky.
So how can FAST engineers build a receiving dish of such epic proportions? It's a challenge that would be impossible without some of history's greatest innovators. Since man emerged from his caves and began building his own homes, most designs have had one thing in common.
Fantastic. Oh, I say, it's simply marvellous.
4 walls and a roof.
Hey!
strike.
But in the 1940s, a revolutionary mathematician, architect and inventor, Richard Buckminster Fuller, had another idea. During the USA's post-World War II housing shortage, Fuller was tasked with creating a cost-effective and easy way to build homes quickly. What he came up with was a geodesic dome house. In southwest England, science communicator Kate Mulcahy is getting a bird's-eye view of how Fuller's geodesic concept can be scaled up to an extraordinary level.
Behind me is an icon in conservation and a feat of modern engineering. These are the biomes, which are part of the Eden project. Now, dangling up here, getting a really good view of them, you can see that while they are dome-shaped enclosures, they're actually covered in a really intricate pattern of hexagons and pentagons with sharp angles and corners. This geometric feat is not just about looking good. It actually has a really important purpose.
Constructed in a disused clay pit in the heart of Cornwall, its designers wanted to house a variety of plants from differing climates, including the tropics.
Measuring 55 metres high, 100 metres wide and 200 metres long, surrounding an area the size of 34 football pitches, the rainforest biome is actually large enough to house the Tower of London.
And this is how Fuller's clever concept makes it all possible.
A geodesic dome is a spherical structure which is made of triangular elements that form a network of circles to create the surface of the sphere. Like the biome here, there's a hexagon formed of triangles, and that creates the pattern that makes the surface of the sphere.
Fuller's argument for using a half sphere or dome to create a house was part of his more for less philosophy. When a sphere's diameter is doubled, its surface area quadruples, but its volume increases by 8 times. It means a sphere creates the largest volumes for the least surface area. And less surface area means less materials, and so cheaper houses.
But the real strength of Fuller's design was that it was made with a series of triangles. Now, the triangle, with its fixed angles, is actually the strongest two-dimensional shape. Now, I want to show you exactly how this works by building one of these using only these. As I'm joining the triangles together, they begin to form the shell of my structure, and the rigidity of each triangle begins to form a tremendous strength. It's only when this final piece gets added that the strength comes together. Now I have a self-supporting structure, and whatever stress I put on it gets distributed evenly across the whole structure.
The beauty of Fuller's geodesic dome design was that the bigger it got, the stronger it became. The only man-made structure to do such a thing.
But how strong is it? It's certainly very light, easy to pick up. The only way to actually test this is for me to climb on top. So, yeah, it's very strong. So we see, Fuller's design definitely works, just like the biomes behind me. Oh, amazing.
Fuller's domes were so strong they could be made of cheap, lightweight material, be prepared from kit form and assembled easily and quickly.
Wow. It's an amazing piece of engineering if you want to build something that's very big, that's very light, and that's very strong.
At the Fast Radio Telescope in China, engineers take Fuller's geodesic method of construction, supersize it, and flip it on its head to create the world's largest uninterrupted dish.
Every time I saw each component built up, I feel very, very excited.
A 1 mile long steel girder ring first forms the outer perimeter of the dish. Surrounding that, 6 100-meter high towers rise up to support and suspend a 30-ton feed cabin built to house the essential cutting-edge receiver technology that will capture the all-important radio waves.
When we propose such a design for a giant dish, nobody believed it can be done. So in order to build such a giant spherical reflector, a geodesic triangular design is the best choice. The dish has been divided into about 4,450 panels.
The panels are supported by an elaborate 10,000-strong steel cable mesh structure weighing 1,600 tons. And after just 5 years of construction, the last 11-meter aluminium triangle panel is lowered into place on the 3rd of July 2016.
This is just an absolutely awesome structure. It's epic in scale. Those aluminium panels are perforated to keep them firstly lightweight, secondly to allow the rain through, and finally to allow the light through. That means the plants can grow on the surface underneath and their roots can get down into the soil and provide a bit of support for this truly enormous structure.
But building the giant dish is just the beginning. To create the most precise telescope ever built, the team at FAST will need to draw on the inspirational pioneers of the past.
Suddenly, the biggest threat came from the sky. Defending against enemy aircraft was virtually impossible.
To create more impossible engineering. Hidden in the mountains of the Guizhou province of southwest China, an extraordinary structure has just appeared. The 500-meter aperture spherical radio telescope, or FAST for short, is the world's largest radio telescope. And physicist Andrew Steele is getting a privileged view.
FAST is massive, and that's ideal for collecting those weak radio signals from billions of light years across the universe. But it also presents engineers with a big problem. FAST is so huge it has to be fixed to the ground.
Smaller radio telescopes have a receiver fixed at the centre of the dish to collect reflected radio waves. The dish is rotated to point at the exact place in the sky under observation. But at FAST, that traditional approach is just not possible.
As you can see from this rather nifty little scale model, you can't just tilt the whole landscape to point fast at a particular galaxy you might be interested in studying.
So, how do you make a telescope the size of FAST point at different places in the sky? For the answer to that seemingly impossible challenge, the team would need to draw on some of history's great innovators. Since classical times, a shape known as a paraboloid has been treasured for its reflecting qualities.
Bashy, bashy.
In 3rd century BC, legend has it that Archimedes,
Thank you very much.
used parabolic mirrors to concentrate the sun's rays and set fire to invading Roman ships.
We'll call it a ray gun.
Okay, boss.
17th century astronomers searched the skies in new clarity by adding such mirrors to their optical telescopes.
Oh, boring.
And early lighthouses used them to beam their warnings out to sea.
Oi, turn the light on.
But it wouldn't be until the first half of the 20th century that engineers would start using parabolic reflectors on a giant scale. High above the Kent coast in southern England, physicist Susie Shee is retracing the route once taken by enemy aircraft.
World War I was the first major conflict involving aircraft, and even though it was a new technology, it had a major impact. Suddenly, the biggest threat to security came from the sky, and defending against enemy aircraft was virtually impossible, as it relied purely on sight.
On clear days, spotting the approaching planes was possible, but at night or in cloudy weather, the enemy had an unacceptable advantage.
And the solution to that problem is these incredible structures.
These monolithic structures once peppered the eastern shoreline of Great Britain.
Believe it or not, these are sound mirrors.
They were the brainchild of pioneering acoustic physicist William Sansome Tucker and were designed to help defenders hear approaching enemy planes that were many miles away.
Here at Denge are some of the last but finest examples of Tucker's work, and they're each a slightly different size and have different structures. So the smallest one points straight out and it collects sound waves that are slightly lower and slightly nearer. The middle-sized one is pointed further up towards the sky. And then finally over there is a 200-foot wall. These striking structures all have one thing in common. They're all based on a curved surface known as a paraboloid. And when the sound waves come in and bounce off the paraboloid, they're all focused down to one point at the centre called the focal point.
Sound waves will hit a parabolic reflector at different points. When those reflected rays meet at the focal point, the sound is amplified.
To demonstrate the effectiveness of these parabolic reflectors, I'm going to attempt to recreate an early warning scenario. So I'm going to place this microphone at the focal point. So about there. Now, the focal point is the point at which, if the sound waves are coming directly towards this wall, the ones that hit the side over there will be reflected right back to this point, and also the ones all the way at the side over there. So all of this area is going to collect sound waves and focus them down to the centre and amplify the sound. So I've got this set up here with a laptop connected to the microphone at the centre of the parabolic reflector, which is about 100 feet away. And all the sound waves are going to bounce off that reflector and be collected by that microphone. And that's represented by the blue curve here, and the red trace is a control microphone that's placed off to one side. So I'm just going to have a quick listen. Now, at the moment, nothing much is happening. The curves are the same. I can't really see any difference. So hopefully, as a plane approaches, the blue curve is going to show us the amplified noise of that plane, and we should see that on the blue curve first before we can hear it out here and see it on the red curve. So I can start to hear something. You can definitely hear a plane propeller.
As the plane approached, listeners on the ground using the sound mirrors would have been able to hear their engines in time to scramble air defences.
So I can definitely see that the blue curve is above the red one in this middle region here. So there we go, we've actually managed to use this parabolic sound mirror to focus and amplify the sound waves from the incoming aircraft. And historically, we could use these sound mirrors to detect airplanes about 15 or 20 miles away.
At the FAST radio telescope in China, engineers have taken all that early inspiration and worked out a truly unique way to turn this seemingly static 500-meter diameter dish into a positional paraboloid.
This thing is enormous. Down here you can see just how ambitious this project really was. It's absolutely enormous. We're driving down into the bowels of the telescope. It's pretty unbelievable that once it was just a little farm in this karst depression, and now it's this incredible structure. From down here, you can really see what's unique about FAST. It uses these actuators to distort the dish. It's got what's called an active reflector. And these are used to tug this huge surface into the exact right shape to collect radio waves. They use 2,000 of these actuators to pull that dish down into that perfect parabolic shape to get the sharpest possible images of the sky.
The system allows astronomers to effectively point paraboloids at whatever area of the sky they want to focus on, making what on the surface looks like a giant static dish a dynamic, moving reflector.
That is the sound of this actuator starting up, and believe it or not, it actually is moving very, very slowly, about a millimetre every second. These actuators allow engineers to move 300 metres of the dish out of that 500-metre total, and that gives you a lot of flexibility. It allows you to look at different parts of the sky. So rather than just looking straight up, FAST can actually scan a region 40 degrees either side of that so-called zenith. And this really is an incredibly innovative solution they've come up with here at FAST.
But being able to distort the dish into a paraboloid is just one step towards a precise reading of the sky. To achieve this, engineers would once more look to the past.
This is awesome. Too much.
To create more impossible engineering. Deep in the Guizhou province of southwest China, engineers have created the most powerful tool in space exploration.
Scientists wanted to create the world's largest telescope to carry on our global quest to understand what's out there in the universe. And that meant they needed to create a huge dish.
Signals from the universe are extremely weak, and so you need a large collecting area to collect as more signals as possible from the deep space. So that's why you need to build a huge dish.
Despite its enormous size, engineers are able to distort the dish surface to create a paraboloid, the perfect shape to collect radio waves. This, however, creates another problem. The receiver needs to be at the center of the paraboloid at all times.
This is the sensor cabin, and it's right at the heart of FAST. Once the radio waves have been collected by this giant dish, they're all bounced into here. Now, in order to track a galaxy moving across the sky, you're going to have to keep moving this to keep it in exactly the right spot to look at the object you're interested in. But because this telescope is so huge, they can't just suspend the cabin on a fixed arm. This thing's actually dangling from 6 steel cables attached to support towers all around the perimeter of the dish. That means we have to know exactly where this thing is and control its movements very precisely to get the best images.
To accomplish that exquisite level of minute alterations to something so large, engineers would need to produce more impossible engineering. Science communicator Kate Mulcahy is finding out that just as early aircraft were fairly primitive, so were the methods of training.
Don't do that. Too far.
Invented in the late 1920s by Edwin Link, the son of a New York-based piano and organ manufacturer,
I can't breathe.
the Link trailer, is considered to be the very first effective flight simulator.
This is awesome. Too much.
Although it's some way short of a lifelike flying experience.
I'm so bad at this. I don't feel any control.
What flight simulation really needed was more realism to recreate the true experience of the sensation of flight.
And in 1964, American engineer Klaus Capell created such a machine. 6 hydraulic legs working in combination were able to emulate the movement of an aircraft incredibly realistically. His motion platform was the forerunner to modern flight simulators.
And here they are. These are super high-tech versions of Capell's motion platform technology. Each of these machines weighs over 14 tons and costs a whopping £12 million. These cutting-edge machines are some of the most advanced flight sims available today. You can see here there are 6 hydraulic jacks or actuators. They're positioned in pairs and move independently from each other. And that allows this motion platform such versatile movement.
Oh my God. I just took off an aeroplane.
I can't see. What do you do?
The specific arrangement of the hydraulic jacks means that, just like a real plane, the cabin can move in what is known as 6 degrees of freedom. 3 linear movements: surge, or forward and backwards, heave, or up and down, and sway, or left and right.
Oh my gosh.
And 3 rotations: pitch, roll, and yaw.
This is a crash, surely.
It's amazing to think that thanks to these 6 hydraulic jacks sitting underneath this crazy simulator, countless lives have probably been saved. With its dynamic range of movement and its pinpoint accuracy, these motion platforms have opened up a world of possibility across a diverse range of applications.
Engineers at the newly created mega telescope in southwest China have taken inspiration from those early motion platforms and adapted them to help hunt the skies with millimeter precision.
Engineers created this, a lightweight cabin that can be moved anywhere across the surface of the dish, a real innovation. It's 10 meters across, looks like a flying saucer, and it's known as the apple of the eye.
Not only does it look like a UFO, it flies like one too. When in operation, the 30-ton cabin, attached by cable to 6 100-meter towers surrounding the dish, is lifted 140 meters into the air.
In here, we've got receivers sucking all that data and sending it back to the control room. But in order to keep those in exactly the right spot, we've got 2 different mechanisms at play. First, we've got those 6 towers out there, which tug this cabin into approximately the right position using the servo mechanisms and those 6 huge steel cables.
Controlled by computers, each cable is individually retracted or released to position the cabin anywhere along a trajectory of 206 meters across the diameter of the reflector. And drawing on Capell's flight simulator, a motion platform is activated.
For that final bit of precision, we've got those 6 hydraulic pistons controlling this platform, which allows the position to be corrected with incredible precision. Those sensors can be located to within 1 centimetre in this 500-metre dish.
The servo mechanisms controlled by the 6 positioning towers combined with the accuracy the motion platform delivers has allowed the engineers at FAST to create a radio telescope of extraordinary sensitivity. But a truly precise reading of the sky depends on the site itself.
The key point to find a home for a radio telescope is the radio frequency environment, the radio quiet environment. So we need to find a remote site.
Human beings make a lot of electronic noise, such as cell phone, microwave. All the electronic devices make magnetic wave. So all this device is generate interference to our telescope.
Engineers narrowed their search to a remote corner of southwest China in the Guizhou province, 170 kilometers from its capital, Guiyang.
FAST is situated in this naturally occurring karst depression, which are a very common feature of the limestone landscape down here in southern China. It's a long way from nearby towns, which might cause radio interference, which would disturb the very sensitive astronomical observations.
But these astronomical observations would not have been possible were it not for the work of an analytical genius from the past. Astronomer Ryan Lynch is at Greenbank Observatory in West Virginia, exploring how a chance discovery unlocked the key to a secret universe.
For most of the history of astronomy, everything that we learned about the distant cosmos came from studying optical light, the kind of light that we see with our eyes. But in the 1930s, the dedication of one man changed all of that.
Whilst working in the development of radio communication at Bell Laboratories in 1928, young engineer Karl Jansky was given the job of investigating some irritating static that interfered with shortwave communication across the Atlantic. In an attempt to trace it, Jansky built a large antenna.
This is an exact replica of the antenna that Jansky built, and it is a work of engineering genius. It's 110 feet wide by 20 feet tall. Now, it doesn't look anything like the curved dishes of the other telescopes that we have on site. I think it looks a little bit more like the wing of an old biplane. But it is an antenna that can detect radio waves from space.
Jansky's antenna connected to a radio receiver. The radio signals received by the antenna were amplified and recorded by pen on a moving paper chart.
The antenna was mounted on a platform sitting on tires that allowed it to rotate, taking a full 360-degree scan of the sky once every 20 minutes. Jansky built this in a field near where he lived in New Jersey, and as it rotated, the locals gave it the nickname Jansky's merry-go-round. His initial findings revealed a faint but persistent hiss that would rise and fall throughout the course of the day. As he continued to analyze the data that he collected over many months, he realized something truly remarkable. The signal was strongest in the direction of the center of our galaxy. Jansky concluded that what he was actually picking up was radiation from the Milky Way galaxy itself.
Jansky had discovered a new corridor to the cosmos. As more precise radio telescopes were developed, groundbreaking discoveries were made, including the greatest of them all, the Big Bang. In 1964, astronomers Arno Penzias and Robert Wilson were able to record the origins of the universe.
Although it would take the work of later astronomers to really kickstart the field, Jansky's work offered definitive proof that radio waves could be detected coming from the cosmos. His directional movable antenna and wideband receiver form the basis of all modern radio telescopes. Jansky, with his plane wing contraption, is considered to be one of the fathers of modern radio astronomy.
Thanks to Jansky's discovery, the team at FAST have created a telescope of extraordinary power, which they hope will one day detect radio waves emitted by extraterrestrial life. But collecting signals from space is useless unless it can be transformed into usable data.
This is the supercomputer we are building for FAST.
And to do that, the team would need to turn to a truly game-changing innovation from the past.
This is actually a computer program.
To build more impossible engineering. Built into the Chinese landscape sits the largest and most powerful single-dish radio telescope on the planet. For FAST astronomer Peng Bo, it never fails to amaze.
It's very excited to see the giant dish from here. It was only a dream to build such a dish, but after 20 years journey, we made it.
As physicist Andrew Steele is discovering, FAST can generate a huge amount of data. And the challenge is to turn those individual radio waves into images.
And this is where the action happens. This horn is part of a beam receiver. It slurps up those radio waves and detects how strong they are. There's only one of these here now, but when this thing is finished, there are going to be 19. That puts it head and shoulders above any other radio telescope in the world. But this poses a huge challenge for the engineers and scientists here at FAST. You've got to take that phenomenal amount of data and turn it into a picture.
So how do astronomers and engineers transform radio waves into images? For that, they would need to turn to a truly game-changing innovation of the past to create more impossible engineering. Science communicator Kate Mulcahy has come to an historic silk mill in northern England to uncover the unlikely beginnings of computer programming.
In the 18th century, garments made from intricately woven fabrics were the height of fashion all across Europe. Looms work by interweaving two sets of thread. The longitudinal threads are called the warp, and the threads running across are called the weft. Now, producing such detailed designs was no easy task, and producers really struggled to meet demands.
In response to the manufacturer's plight, a French weaver called Joseph-Marie Jacquard invented a machine that would keep production on track and completely revolutionize the industry.
And this is it. This is the Jacquard loom. Now, Jacquard had achieved something that no other weaver had done before him. He combined the best in weaving technology to make this stunning machine. Amazingly, all of these complex mechanisms are actually governed by a few simple cards. This is a card cutter. Skilled workers would use this to translate complex patterns into a language that the loom could understand. The first step would be to copy the pattern onto squared paper, a bit like this. Then for every piece of the pattern that's in a square, a hole would be punched in a corresponding position on my card. Each punch card represents only one line of weave, which is pretty amazing. The next thing we need to do is to take my card, put it into the loom, and that's when the magic really happens.
As the cards enter the head of the machine, they're pressed against rods protruding horizontally from the loom. Each rod controls an individual warp thread. Where there is a hole in the card, the corresponding thread is lifted. In this way, the cards dictated the pattern being woven.
One pattern could take thousands of cards. Brilliantly, if you needed to change or amend your pattern, you simply need to load more cards. Whilst a hand loom operator could produce around 2 inches of fabric a day, the amazing Jacquard loom could produce 30 times as much. And it only required one person to operate it.
The hole or no-hole card system is essentially an early version of binary code. Still the basis of all computer language, and this method of programming a machine later caught the attention of computer pioneers. Inspired by the marvellous weaving machines from France, American inventor Herman Hollerith developed similar cards as a method of storing the 1890 US Census information. Holes denoting specific meanings, for example age, gender or marital status, could be read by Hollerith's tabulating machines, allowing census data to be collated 10 times faster than previously.
In the 1960s, computer programmers were using punch cards to create, edit and store computer programs. Incredibly, this is actually a computer program. It's a series of instructions encoded in holes telling the computer exactly what to do. Now, just like the punch cards we looked at earlier, where each card represented a single line of the pattern, here, each card represents one single instruction for the computer. So a computer program could end up being made up of thousands of cards.
In the 1980s, punch cards were largely phased out in favour of magnetic tape and discs that were able to store more data.
Punch cards were the first big step towards building a computer that could be programmed to do just about anything you can imagine. They gave programmers the license to dream big. Suddenly, the possibilities were endless, from connecting the planet to better understanding the universe.
Thanks to the work of Joseph Jacquard and the pioneers of computing, the team at the Fast Radio Telescope in China can use powerful programming to turn radio wave signals into images.
Here, this is the supercomputer systems we are building for FAST.
Built alongside the radio telescope is Fast Central Control. Here, astronomers the world over will be using the vast amounts of data to unlock some of the mysteries of our universe.
The modern radio telescope always try to visualize the radio signals you detect from the telescope. With the computer, you can display these signals with different light curve.
Radio waves travel through space like light, but are invisible to the human eye. To turn these signals into images, astronomers use computer software to label each individual wave received with a color code, depending on the signal strength. The resulting buildup of colors forms a pattern, which in turn becomes an image identifiable to the human eye. To create those radio images, astronomers at FAST will need to process a lot of data.
We expect FAST can generate 40 terabytes per night. So we need a huge amount of a storage system. So here we have roughly 1.6 petabyte storage. And also we have a high performance computing system to process the data. We can start to try to use telescope to explore a completely new universe that have never been explored before. We are expecting to see lots of the new things.
This is very exciting for astronomers, also I think for the human being, because they'll know some new knowledge about the unknown, about the universe.
Officially completed in September 2016, FAST is now ready to begin searching the skies further and deeper than ever before.
FAST is going to revolutionise radio astronomy and transform the way that we look at the universe. We just didn't know it was possible to build a dish this big, so we didn't know that you could make a machine this accurate and this powerful.
For astronomer Peng Bo, it's the culmination of a lifelong dream.
I'm very proud to be a member of this team to build a giant radio telescope. So I'm very proud of the achievement you see today here.
By drawing inspiration from the great pioneers of the past, adapting, supersizing, and developing innovations of their own, the designers, engineers, and workers at the FAST telescope have succeeded in making the impossible possible.
FAST is going to allow us to scan more of the sky more quickly than was ever possible before. It's going to give us fresh insight into why the universe looks the way it looks and where it came from. And even more than that, this huge geodesic bowl, buried deep in the rugged South Chinese countryside, is just an engineering marvel.